which is smaller than mu, it forces mu to be larger than that. But then what? You take that inequality, you raise it to the kth power. We get a sub k is less than mu to the k. Which then what? What does that mean? You guys tell me, what's the sum k equals 0 to infinity of mu to the k? I say it's 1 over 1 minus mu. Why do I say that? Exactly, this is a geometric series. So we just showed a geometric series which converges, right, has terms which are larger than our given series a sub k. Therefore what? Hence by direct comparison, right? Direct comparison test, the series a sub k converges. Now, the proof of case 2 is very similar. The proof of case 2 is very similar. You do direct comparison to a geometric series which diverges. All right? I'll let you read that in the book. I think if we do this case, it suffices for here. Yeah? But this is the root test. There's one other significant test. Well, there's several actually. That's not true. Ratio test. What's the ratio test say? It says if we have a series with positive terms, oh, check that out, with positive terms. So if you got a series with non-negative terms, which is the right tool to try? Yeah, one or the other. Definitely not this one, right? If it's got 0 as a term, don't use the ratio test. And if we have that the ratio of ak plus 1 to ak goes to lambda, then, again, case 1, if lambda is less than 1, then the series converges. 2, if lambda is greater than 1, then the series a sub k diverges. I refuse to write case 3, but case 3 says that if lambda is equal to 1, the ratio test tells you nothing. It's inconclusive in the case that the ratio works out to 1. All right? You guys seem too tired for a proof at the moment. I'm not going to show you the proof at the moment, but it is on page 595, and you know what it again involves? You take the limit that you're given, it suggests an inequality, and you know what you compare to? That geometric series. So again, it's the geometric series that really proves the ratio test when you get down into it. Let's look at some examples. How many examples did I already do? I don't remember. I think this is the third, right? So here's one. Sum k equals 0 to infinity of 1 over k factorial. So what do you think the right tool is here, root or ratio? My example 4 will be the sum, and I'm tired of k, so I'm going to use n, 1 over natural log of n to the n power. N equals, I better do 2 to infinity. N equals to 1 is troublesome. I've been writing these convergence and divergence tests in terms of k today, but you could just as well express them in terms of n or some other letter, right? One of these is good with root, one of these is good with ratio. Which one's the root? This just screams at you root test, right? This is actually a ratio test. Let's see how it goes. So here, a sub k is 1 over k factorial. It does not, because 0 factorial is 1. So a sub k plus 1 over a sub k is 1 over k plus 1 factorial divided by 1 over k factorial, which, do the algebra here, gives me k factorial divided by k plus 1 factorial. But how did we define factorial? Recursively, right? So like k plus 1 factorial can be rewritten k plus 1 times k factorial, right? So what happens? The k factorials be canceling, right? We get 1 over k plus 1, which of course goes to 0 as k goes to infinity. Hence, the sum, k equals 0 to infinity, of 1 over k factorial converges by ratio test. So rho in this case, excuse me, lambda in this case was equal to 0, right? Is 0 less than 1? Yeah. This other one here, we identify a sub n is 1 over the natural log of n to the n power, right? Thus, a sub n to the nth root power, right? 1 over nth power is what? So they just leave you 1 over log n. What happens as n goes to infinity of 1 over log n? Yes, log n goes to infinity, so what happens with 1 over log n then? It goes to 0, right? Hence, the sum, n equals 2 to infinity of 1 over the natural log of n to the n power converges by root test. With rho equal to 0, which of course is less than 1. So what are the tools in our toolbox at the moment? Let us recount what we already have to play with. We have direct calculation, right? Telescoping series. First thing we found, we could actually calculate for something that had that looked, if the partial fractions works out for us, we can sometimes calculate by a telescoping series. That's one thing. Next up, geometric series. We have the geometric series result. If our given series is geometric, we can determine its convergence or divergence looking at it like that, right? We also know that a sum or a scalar multiple of series is related to the original one. So sometimes you have something that's like not just one geometric series, but like a sum of a couple of ones, and that you can also deal with. Past that, we had the integral test, right? The integral test is another convergence-divergence test. That gave us the p-series result, right? So we have p-series result. Then we talked about using p-series to do direct comparison test. So we can use direct comparison test to compare to the p-series or the geometric series. After that, the limit comparison test. Very nice, very useful for series with positive terms whose quotient you can, the limit comparison test we talked about at the start of today. Then the root test, and now the ratio test. These are the tools we currently have at our disposal. What's left? All right. Well, next up, and I won't present this today, but I'm just going to tell you it's there. Next up is the concept of absolute convergence and or conditional convergence in the alternating series. An alternating series is one that goes plus minus, plus minus, plus minus in terms of the terms. It turns out that if you have an alternating series, sometimes some people will say that the alternating series has the wishful thinking. We teach you it's not enough for something to go to 0 to make it converge. For an alternating series, it actually kind of is. If you have an alternating series with terms that are going to 0 in terms of their magnitude, it forces a certain cancellation to happen, and so an alternating series converges. So alternating series or absolute convergence, that's really the only last convergence divergence test we have to work with. Let's see here. So since I kept you a minute over the other day, let's add in a couple minutes early today. That's a good place to stop. So many more examples to see, obviously. Thanks, guys. Got it.